Have you ever stopped to think about what goes into making one of those iconic chrome rims? Today, we're going behind the scenes with DMG Mori, one of the world's most respected machine tool manufacturers, to watch how a Harley-Davidson wheel rim is born. The process begins with a solid aluminum alloy forging, a rough, cylindrical blank that barely resembles what it will become. The first operation is setup and center hole drilling. The part is mounted on the machine's primary spindle and a precision center bore is drilled. This becomes the datum reference for every subsequent operation. Get this wrong and nothing else will align properly. From there, the machine transitions into rough turning of the outer diameter and the inner rim profile. Large amounts of material are removed quickly. You can see the aluminum chips flying as the cutting insert bites deep. The DMG Mori spindle delivers up to 10,000 RPM, maintaining consistent surface speed as the diameter changes. Next comes the spoke milling phase, and this is where it gets truly beautiful. The machine's B-axis head rotates into position, and a precision end mill begins carving out the distinctive spoke pockets. This isn't just aesthetic. The geometry of each spoke is engineered to distribute load evenly across the rim. The DMG Mori's simultaneous 5-axis interpolation means the cutter follows a perfectly smooth path around every contour, leaving a surface that barely needs finishing. The rim is then transferred to the secondary spindle, a seamless handoff with zero repositioning error, and the opposite face is machined. The valve stem hole is drilled, the bead seat surfaces are finish turned to tight tolerances, and the hub bore is bored to the exact fit needed for the bearing. Throughout the process, the part rotates between different machining perspectives: face milling, contour turning, cross drilling, each operation building on the last. The machine's integrated measurement probes check critical dimensions in cycle, so any correction happens automatically before the next cut. The final finishing passes leave a surface roughness measured in RA 0.8 or better, smooth enough that the subsequent chrome or polish process flows on like water. The finished rim emerges from the machine looking less like manufactured metal and more like a piece of jewelry.
What you're looking at right now is the Fabrication 4-roll plate bending machine. And folks, this thing is an absolute marvel of modern engineering. Fabrication is an Italian company with over 60 years of experience, and they've built some of the most advanced plate rolling equipment on the planet. This particular machine is designed specifically for the wind energy industry, where precision isn't just preferred, it's absolutely required. So how does a 4-roll machine differ from the older 3-roll designs your grandfather might have seen in a steel shop? Great question. The secret is in that 4th roll. The additional bottom roll gives the machine the ability to pre-bend both ends of a plate in a single pass. No repositioning, no flipping, no wasted time. That alone saves hours on large industrial projects. Now, here's where it gets really impressive. The plates being processed here aren't thin little sheets. We're talking steel plates up to 6 inches thick and over 30 feet long, destined to become the towering shells of wind turbines. Each cone section must be rolled to an exact diameter and taper. Tolerance is measured in fractions of a millimeter, because when these sections are stacked 300 feet in the air, even the smallest error compounds into a serious structural problem. The Fabrication system integrates CNC automation with real-time feedback sensors that monitor plate position, roller pressure, and curvature continuously throughout the bending cycle. The operator sets the parameters on a touchscreen interface, and the machine does the rest, adjusting pressure dynamically, compensating for springback in the metal, and verifying the final geometry before the plate ever leaves the rollers. This is ring rolling, and the company behind this extraordinary operation is SMS Group, a German industrial powerhouse founded all the way back in 1871. Over 150 years of metallurgical expertise, and they're still setting the standard today. So what exactly is ring rolling? It starts with a solid steel billet, a thick, cylindrical chunk of raw steel that's been heated in a furnace to around 2,200 degrees Fahrenheit. At that temperature, steel becomes workable. Not liquid, but soft enough to be shaped under enormous mechanical force. The heated billet is first punched to create a donut-shaped preform. This rough ring is then placed between two precision rollers on the ring rolling mill. The main roll, called the mandrel, applies pressure from the inside, while the outer drive roll presses from the outside. As the ring rotates between these two forces, the wall becomes thinner and the diameter grows, all while the ring maintains its circular form. SMS Group's modern ring rolling mills add a critical refinement. Axial rolls positioned above and below the ring apply simultaneous pressure, controlling the height of the ring and ensuring it doesn't flare outward. The entire process is governed by computer-controlled hydraulics that adjust pressure and speed in real time. What emerges from this process is a seamless steel ring. No welds, no joints, no weak points. That seamless quality is exactly why ring-rolled components are trusted in jet engines, nuclear reactors, offshore drilling platforms, and heavy mining equipment. SMS Group produces rings from just a few inches in diameter all the way up to rings over 3 feet across. Each one is a testament to the kind of old-world metallurgical craftsmanship, refined and supercharged by modern technology, that keeps the world's most demanding machines running safely.
This is the production of a drive housing, the protective shell that surrounds the gears, shafts, and bearings inside a heavy industrial drivetrain. These components appear in wind turbines, large agricultural machinery, mining equipment, and heavy vehicles. They need to be dimensionally precise, mechanically strong, and capable of withstanding decades of vibration, thermal cycling, and mechanical stress without failure. The method being used here is sand casting, one of the oldest and still most versatile casting techniques in manufacturing. But make no mistake, today's sand casting is a far cry from what you might imagine from a high school shop class. It begins with pattern making. Engineers design the drive housing in 3D CAD software, then use CNC milling or 3D printing to produce a precise pattern, a physical replica of the final part, slightly oversized to account for metal shrinkage during cooling. This pattern is pressed into specially treated molding sand, a mixture of silica sand, clay, and chemical binders to create the two halves of the mold, called the cope and the drag. Inside the mold, sand cores are placed to form the internal cavities, the hollow passages, bolt holes, and gear chambers that would be impossible to machine after casting. These cores are engineered to be strong enough to hold their shape under the pressure of molten metal, yet brittle enough to be broken out after the metal solidifies. Now comes the dramatic part. The furnace, typically an electric arc furnace or induction furnace, brings the raw iron or steel to temperatures exceeding 2,800 degrees Fahrenheit. The molten metal glows a brilliant orange-white as it's poured carefully into the mold through a system of gates and risers, channels designed to control the flow of metal and prevent turbulence, which can introduce air bubbles and weaken the final casting. As the metal fills the mold, the risers act as reservoirs, feeding additional metal into the casting as it cools and contracts. This is a critical detail. Without properly designed risers, a casting can develop internal shrinkage voids that are invisible from the outside, but catastrophic under load. After cooling, which can take anywhere from several hours to an entire day depending on the size of the part, the sand mold is broken away and the rough casting emerges. It's then shot blasted to remove sand and scale, and sent to the machine shop where CNC milling, boring, and grinding operations bring it to its final dimensions, tolerances sometimes as tight as a few thousandths of an inch. What began as a bucket of sand and a ladle of molten iron has become a precision-engineered component, trusted to protect the heart of a machine working 24 hours a day, year after year.
If you've ever wondered how the massive curved steel shells of pressure vessels, storage tanks, wind tower sections, and ship hulls are formed, this clip has your answer. And the machine at the center of the story is one of the most impressive bending machines you'll ever see. The Akbend AHS 30-45, a 4-roll plate bending machine built by Akbend, a Turkish manufacturer that has become a genuine world leader in heavy bending technology. 4-roll bending is a process that has been around in various forms for well over a century, but the modern computer-controlled version is something else entirely. Where older 3-roll machines required the operator to flip and refeed the plate multiple times to complete a cylinder, the 4-roll design bends the plate in a single continuous pass. That's a game changer for productivity, precision, and safety when you're working with steel plate that can be 30 millimeters thick or more and several meters wide. Here's how the AHS 30-45 works. The machine features 1 top roll and 3 bottom rolls, 2 side rolls, and 1 lower pinch roll. The side rolls are what give this machine its power. They can be positioned independently at precise angles, creating a continuous bending moment across the full width of the plate. The process begins with plate loading. The heavy steel plate, which might weigh several tons, is positioned between the top roll and the pinch roll, which grips it firmly and feeds it through in a controlled manner. The operator, or the CNC system, sets the position of each side roll according to the desired bending radius. The plate then passes through the machine, and as it does, the rolls apply progressive, even pressure across the entire width, curving the metal smoothly without local stress concentrations. One of the AHS 30-45's most impressive features is its pre-bending capability. Traditional plate rolling always leaves straight, unbent sections at each end of the plate, the so-called flat ends, which then have to be pressed separately. The 4-roll design minimizes this problem significantly because the pinch roll grips the plate right at the end, allowing the side roll to begin bending almost immediately. The result is a much more consistent cylinder with minimal flat areas. The machine's hydraulic drive system provides enormous force. The AHS 30-45 is rated for plates up to 45 millimeters thick in standard steel, while its CNC control system allows operators to store bending programs for repeat jobs, call them up instantly, and execute them with confidence. Sensors monitor roll positions in real time, with feedback loops that compensate for material springback, the natural tendency of steel to partially unbend after pressure is released. After bending, the formed shell, now a cylinder or cone, is tack welded to hold its shape, then moved to a welding station for final seam welding. Dimensional checks verify roundness, diameter, and straightness to the drawing tolerances.